Yeah. So this is the first half. Yeah, this is actually this is the motivation of open source hardware in China. This is because we are inspired by open source software ecosystem in China. This is and another motivation is open source can reduce the barrier of chip industry. So that is our envision. We are envisioning the open source chip ecosystem can lower the barrier of chip development by saving time to market and the cost of IP, EDA tools, and so forth. So here is our perspective on open source chip. So there are 3 levels. Yeah. So this is open ISA, open documents, open source codes, and open framework, open flow, and open tools. So basically, this is the 3 levels. Yeah. One is open ISA. Level 2 is open design and implementation. Level 3 is open framework and tools. And the last time I mentioned, I was introducing the Xiangshan project. Yeah, this is the motivation. So we are going to build a leading. Our goal is to build a leading platform with agile development tools and flows. Xiangshan is a high open source high performance processor. So we have already developed the 2 versions. This is the first generation called Yanxihu. And this is the 2nd generation called Nanhu, is another lake. And the 3rd generation is ongoing. Yeah, Xiangshan is open sourced on GitHub and already attracted more than like 2,700 stars and more than 300 forks on GitHub. This is the first generation. It's already taped out, and it can run 1 gigahertz, and it can run spec CPU, and also it has some like a Ethernet SD card, so we can boot Linux like Debian on Xiangshan chip. It can run GUI program from X11 forwarding. The 2nd generation is called Nanhu. The code name is Nanhu, and it targets 2 gigahertz at 14 nanometer technology. We have made 4 major changes from front end, back end, new cache, and also this is a dual core SoC with PCIe and USB and so on. Yeah, the performance of Nanhu is approaching, I think it is approaching to A Cortex A76. But this is just for, I mean, the performance with if we compare L and power, so we still lag far way behind ARM Cortex A76. So we made an important decision on the Xiangshan project that we decided to use Chisel to development Xiangshan. So last time actually I also introduced our experiments, 2 sets of experiments between Chisel and Verilog. Yeah, and also we have many experience in using Chisel to build real chips. This is the experiment, one experiment on comparison with Verilog and Chisel, and we assign the same task to 2 guys. One is engineer, another is undergraduate student, and their task is to design an L2 for RISC-V rocket chip, the rocket chip core, and the result is that the Chisel is more productive than a Verilog by like 14 times, and with only 1/5 lines of code. Yeah. And then our second experiment is to translate the Verilog codes written by the engineer into Chisel code. And this is done by a junior student, also undergraduate student, who never knew Chisel. And actually, he was learning by doing. And this column is the initial results written get the initial results done by the junior student. So we can see that the frequency, the power, and some resources are already better than the Verilog version. And this column is actually improved by actually it's under the guidance or the help with a PhD student who has many who is more who has more experience in Chisel than the junior student. Then we can see that most metrics are better than the Verilog code. So actually, according to this experiment, we can conclude that actually Chisel can achieve even can achieve the better PPA than Verilog for this task. So the student actually, the engineer finally accepted the result, and he said that Chisel probably is a promising programming language for hardware development. I introduced our results to Huawei, and they said your engineer only has 5-year experience. Actually, we have 15-year experience. We have engineers with 15 year of experience. So probably you should compare your student with our engineers. But our engineer is he is an expert in cache, and now he is a PhD student in Yale University, and he has quite a good expertise in computer architecture. And after 2 years, I talked to Huawei guys, and they said that they already formed a group working on Chisel library, that they are going to build some libraries written in Chisel. So actually, Huawei is already using Chisel. Yeah, this is our decision. And actually, I think for this decision, we actually conducting agile design just by adding a new abstract layer. This layer is kind of like an object with object-oriented programming, similar to software engineering. So with this methodology, design becomes easier. So we can see that agile design is easy. So we just use a new language. It's easy to do agile design. The problem here is agile verification. When we can build a new design with those agile language, such as like Chisel, we write codes very fast, but verification becomes very challenging. So we also proposed an agile verification flow and build a bunch of tools. Those tools are responsible for two roles. One is functional verification. Another is the performance verification. So next, I will introduce how we use those tools to do like functional verification and performance verification. First is the agile functional verification. the goal of this step is to verify if our design is correct or incorrect. So this is a circle. We needed to do like a back detection. We needed to do like context preservation, and next is we needed to do troubleshoot and fix bug. Finally, we perform regression testing. So this is a circle, and under this circle, we have built several tools to accelerate this cycle, so that we can do more. We can do functional verification more efficiently. Here, just one example how we accelerate, how we speed up the verification, functional verification. For example, this is just one case. We know that for conventional verification, we need to most of the time for example, many companies, they do verification by verifying the consistency of the outputs of the DOT and the REF, which means the design on the test and the reference model, just like the left part. So in conventional verification, the reference model requires very details in implementation. For example, like buffer size and replacement policy and so on. And when we do agile design, so we found that it's very easy to generate the DOT, since with language like Chisel, it's very easy to modify design and then generate new design, new DOTs with the variable code. Since Chisel can generate the variable codes, it's very easy to generate new designs for this part. And but this brings some new challenges, since for each design, for each DOT, we need a reference model. We need a reference model, a corresponding reference model. So actually, this is raise the more burden of verification engineers. So that is actually that is why industry and many companies actually they don't have the interest in using Chisel-like language, those agile design, since this work actually brings new burden, even heavy burden on verification. Well, but our we proposed we are inspired by programming language. So for example, Professor like Baba Kliskov, in his talk, he talked about some key ideas of programming and software engineering. For example, what is correctness? What is golden reference? So then we come up with the insights that actually, when we say correctness, a design is correct. So the inventory rule is specification. Actually, specification, if a design matches the specification, the behavior of specification, then we can say this design is correct. So specifications are the eventual golden reference. This is one insight. Another insight is for actually a given design, a given specification can lead to diverse implementation. For example, for cache, we have a cache behavior, but actually they can use different replacement policies. So, but it will not affect the correctness of specification. So in this case, we mean that once the design matches the behaviors of specifications, then different implementations are allowed. The next question is how to describe specifications. Actually, there are different ways. For example, like natural language. Actually, many specifications are written in natural language. Yeah, natural language is a high level abstraction. It's very flexible and easy to understand for human. And besides natural language, there are also other ways. For example, like the SEER model proposed by Cambridge University. So this is a more formal model, and there are more restrictions. And then this model can be used to generate many different languages, and with like a formal restrictions. This is another way of describing specifications. And also we can use like a Verilog, system Verilog, to have many implementation details. So this is also a way to describe specifications. Anyway, with those ways of this specification describing specifications, we argue that we can also add some rules to describe the spec. So then we propose the rules-based agile verification. So the general idea here is we use rule to describe behaviors defined by spec. And here is some example. For example, this is one rule. The DOT and the reference should have the same architecture states when they execute the same number of instructions. This is just one rule. It's always it is true is defined by the spec. Another rule actually is also defined by, for example, in RISC-V for the TLB refill. So in this case, the rule can be defined as a page fault exception can be triggered in DOT even if it does not occur in reference model, which means when you have a simplified reference model, and then it can also matches a complicated DOT. So this is just a two rules example, and then we use the probe to get information, to collect information in the DOT, and those information will be sent to the reference, the REF. And here are many rule checkers to check the information collected by the probes and the information generated by the reference. So in this way, we can just use one reference model with multiple rules to verify different or multiple DOTs. In this way, even you can generate many many DOTs, since we can still use just one reference model for verification, and then we can speed up the process of verification. here is the concrete implementation of the Agile verification. Here, this is we define some probe. There is a probe. This probe can be inserted into the Xiangshan codes, for example, in cache, in TLB, in reorder buffer, and like this is inserted into different placement of the Xiangshan code, source code, and those probe can collect information when the RTL codes of the Xiangshan is running, is executed in an RTL simulation or RTL emulator. And then here is the rule checkers. For example, this rule, DOT should have the same architecture states when they execute the same number of instructions. Then we will here is we do architecture state checker here. We just use a memory compare, do memory compare of those states. Yeah, this is just one example for the Agile functional verification. Another verification is for performance. How can we know if a modification achieve faster performance or slower performance? So for example, when we introduce a new feature, how can this new feature brings benefits or negative impact? So when in here, we also have a circle. So for Agile performance verification. So we introduce new features and then we do performance testing. We run a bunch of testing cases, and then we get some result. We do performance evaluation with those tools. Some tools are written by ourselves with the red rectangles, and some very popular tools used in the computer architecture, like a Variator or SimPoint. And then we do performance analysis to find the bottleneck of the new feature introduced by the new features. We also use the top-down analysis methodology to find the bottlenecks. Yeah. So in this way, we use the RTL-based design space exploration. You know, we know. I think most design space explorations are based on simulators like Gem5. But here we don't use Gem5. We just use the Chisel source codes. So we use one version of Chisel codes. This is the RTL codes to do tape out and also do design space exploration. So this is since we found that Chisel is everything you need. So you can just like what can you see? What you get is what you done, what you written. And since writing Chisel codes actually is not more complicated than writing C codes. So actually it's very flexible and very fast. But the problem is the shortcoming is very slow. When we run RTL simulator or RTL emulate, it's very slow. Usually slower than like a cycle accurate simulator written in C, for example, like Gem5. So how to deal with this problem? So we can see there are different ways of performing RTL simulation. One method is we use emulators, but those kinds of emulators are very expensive. For example, always like millions of dollars. And another way is we can use the FPGA to do RTL emulation. But FPGA has a big issue, or is challenging for troubleshooting. FPGA is easy to expose bugs, but it's not easy to pinpoint the bugs, well, the location of bugs. And validator, I mean, the software-based RTL simulation is a good way to do bug detection, but it's very slow. So here our goal is to speed up software-based RTL simulation. So there are our results. With original RTL simulation, usually we compile the Xiangshan codes in 20 minutes, but it can run only 2 kilocycles per second. So if we want to run the whole spec CPU workloads, it takes more than 1,000 years. FPGA is dramatically faster. It takes 5 hours to compile, and usually takes 7 days to complete all spec CPU 2006 workloads. But with our approach, we can compile all the Xiangshan codes in 20 minutes, and with enough servers, we can get the spec CPU the performance in the performance in just 5.5 hours. Yeah, this is our approach. So our approach, actually, there are 4 steps. One step is we use like SendPoint. First we collect instruction slides, and we run the spec CPU workload in a very fast instruction simulator that can run like 300 millions of millions instruction per second. It's very fast, so we can run the spec CPU, all the spec CPU workloads in just like 2 days, and we get all the instruction traces, and we then cut the traces into slices. Each slice has like 50 millions of instructions, and then we use some machine learning algorithm to do clustering, to do classification, and to find out representative slides. And next is we do a checkpoint, a generic checkpoint. This checkpoint can translate, can convert the architectural state from fast simulate into RTL emulators. So this is this generic checkpoint is very useful to allow us to run those program slices into different platforms. Some are on like GIM5 simulators, sometimes on GIM5 simulators, sometimes on RTL emulators. So it's all connected. And then we get some result of the performance results of those programming, of those program slices. And finally, for the step 4, we reconstruct all those program slices to form the whole program's performance by combining some combining algorithms. So with this 4-step, we get those results. So this is the results of all 29 spec CPU workloads. And we can see that this is the dark blue bar represents the RTL simulation. And for example, for this, the dark blue bar, and the yellow bar is the result obtained by FPGA, and the blue bar, the green bar is the result measured on real chips. So we can see that for most workloads, those performance are almost the same. Those 3 bars, which means our approach is actually is effective. But sometimes the FPGA for this case, FPGA is slower. This is because of the I/O for the I/O intensive. Yeah. So according to this chart, we can see that our approach can achieve almost the same performance as the FPGA emulation, and also the same performance as the real chips. And also, according to this chart, we can get the result. We can get the conclusion that the performance of the second generation is about like 50 improvements on the first generation. Yeah, this is this gray, this brown bar. Okay, so finally we formed a whole agile development infrastructure for Xiangshan. Here, this is the flow, and this is the tools we have built for Xiangshan. And from our perspective, and I think Xiangshan, this agile development infrastructure is the key outcome of the Xiangshan project. And now we already open sourced this infrastructure to all the community, and the many companies are interested in this infrastructure, and they actually joined to us to develop Xiangshan, the third generation Xiangshan. So I think the infrastructure actually is more important than the Xiangshan architecture. This is just like this part of the iceberg. Yeah, the underwater part of the iceberg. Okay, so the conclusion here is I think Xiangshan achieves level 2.5. The Xiangshan is unable to achieve level 3 yet, since we still need to use a lot of commercial tools, commercial EDA tools. Although we have built many agile tools, many tools for agile verification, but we still need tools from like Synopsys or Cadence or Mental Graphics. So I think we hope in the future we can achieve the level 3 with all open source EDA tools. Okay, this is the Xiangshan project. Next, I will introduce.
Can we open the floor to some question about the first part?
Okay, yeah, no problem.
If somebody Actually, I got one question which is not really related exactly, but somebody asked how the COVID-19 affect your operation and especially the people cannot move, etc. If it has impact.
Yes.
Yeah.
Okay, so for the architectural development, I think the COVID-19 doesn't generate negative impact, but for manufacturing, yeah, it did it did has some impact. For example, we originally we will tape out the second generation of Shanghai in this May, but Shanghai was locked down over the past two, I think past 3 months. So we cannot tape out until this August. Yeah. So it's delayed. The tape out of the second generation of Shanghai was it is delayed by 3 months.
Mm.
Yeah.
Maybe I have one more question.
Okay, yeah, right.
Okay, so first, this was very, very interesting. Thank you for sharing all this information. So basically, I wanted to ask you about, the translation from, going from chisel to system Verilog and then doing synthesis. So, going through multiple level of description languages may also introduce several challenges. So for example, you need to maintain several databases. If you are going into practice and you are now in the stage of doing ECOs, or you need to do bug fixes. And, in normal chip tape out and sign off, you maintain like 2 databases. One is the Verilog or system Verilog database, and the other one is the gate level or the netlist or whatsoever. So now, from my experience, I can say that the challenges that I see when going through multiple levels of hardware languages is that you need now to maintain another database, another language, and sometimes in order to make all the database coherent, and you need to go to do the fix in chisel, and then you need a certain way to do like formal equivalence checks or something like that. Maybe you can highlight about this based on your experience. How do you see these challenges?
Yeah, this is a very good question, great question. So actually, we have built, I think already 10 chips with chisel. And for the first chip, yeah, we do encounter some challenges in, for example, like ECO. It's quite a challenge since it's not easy to figure out which path, the path, even the variable name. Yeah, it's quite a challenge since once you modify a line of even one line of chisel code, and the variable code is modified actually dramatically. Yeah, even there's no similar variable names. But then we found actually there are many. This is not the major challenge. Actually, or in other words, it's easy to solve this problem. Finally our students figure out a way to solve this problem. So it's quite easy to make some mapping from the chisel variable to Verilog codes. So then after currently from our development of Xiangshan, we can do ECO very flexible and very efficient. Yeah. So and we also help some start companies in China. So like they provide they offer ECO products. Yeah. And previously they don't actually they do ECO on those variable codes written by engineers, and now they can also do ECO on chisel generated variable codes. It's easy to use that. Yeah.
That's very interesting because, you know, the standard tools like formality of synopsis and the logical equivalence code of cadence need certain entry points, like certain map files in order to do the formality equivalence, formal equivalence between the RTL and gate level. That's why I thought it's standard, but okay, that would be very interesting to hear about.
Yeah,
okay,
it's kind of all pass. It is able. We all pass those like a DRC or or those tools provided by Synopsys or Synopsys. Yeah, it's this is easy to do, and we also build a tool that is able to translate like a waveform into chisel codes. So then, if for example, when we do RTL emulation, and when there is a bug, and then we get like waveforms, yeah. But we have already built tools to translate these waveforms into chisel codes. This is very easily, it's easily done by inserting a transform into the chisel actually chisel photo. No, so chisel just like an LLVM, you can write your own path into chisel to enhance its functionalities.
Yes, got it. Okay, thank you.
I have a question about the sim point and the methodology of using checkpoints, etc. It looks like that all these techniques are good for signal processor, but they are much less effective when you have parallel events like snooping and parallel code, etc. How you handle with the parallelism?
Yeah, you are right. So currently, actually, we are unable to deal with power issue and so forth. So that is our next actually next goal. Actually, this is I think this infrastructure is also also open, and we encourage other research groups to contribute their tools into the framework. I also talked to Trevor Carson from the National University of Singapore. So yeah, he is working on like power estimation, power tools. So then I think I hope one day his tools can be integrated into this this flow. So, but currently, yeah, we don't have they don't have the capability of like power estimation and so forth. Yeah.
Okay, thank you. If no other question, we can move to the second part, which I'm sure will be as exciting as the first one.
Okay, thank you. So the second part is the One Student, One Chip initiative. So I launched this this initiative in 2019, but actually I did some work, did some survey work in 2017. At that time, 5 years ago, I did a survey of 10-year ISCA papers. There are 483 papers from ISCA conference over the 10 years, and I collect all those data. And for example, this is the first authors, and this is where did they go. For example, which country did they stay after graduation? Yeah, sorry. And here is the result. Where were those talents from, and where did they go? And we found that only 4% of talent architects worked in China, while 85% stayed in the US. Yeah, so here is the result. But if you look at where were they from, we can see that probably like 20% of those talent architects are from China. Actually, you mean in China, actually, there are many talents, but they just don't have the opportunities to do those, to get a trained or to do those kind of computer architecture research. So how to solve this problem? And actually, I was seeking some solutions and how to improve the talent in terms of skills and qualities. I was inspired by the Moses project. Yeah, this is already 50 years ago, and it's actually is funded by DARPA. The Moses project, when I saw the Moses project, actually, I was kind of stunned. Why? Because it was said that in 40 years ago in the US, there were less than 100 students and faculty conducting silicon research at that time. Oh, I was surprised to see this data. But today it definitely not. So how the US changed this situation? I think the Moses project played a very important role. Yeah, and DARPA launched the Moses project in 1981, and now till now, Moses has delivered chips for more than 60,000 designs, actually, which trained hundreds of thousands of talents. Yeah, this is very important. As we know, like Moses supported projects like the RISC project in Berkeley and the MIPS project in Stanford. But for comparison, let's look at China, the situation in China. So around 2010, we will see that the education in China was kind of embarrassing. There was a study on the scores of computer system courses in the national entry examination of a graduate school. Yeah, the results show that the average score of a computer organization is only between 34 to 49. So the first score is 100. Yeah, it's 100. And so this means like it's almost the average score is less than 50. Operating system is a little bit better, but it is also only between 41 to like 54. So there we can see the problem here is we all recognized that there was a big gap between the theory, the concept, and the practice. Yeah, in China, many computer system courses, students only memory concepts rather than practice. And also teachers teach knowledge in a disconnected manners. So those knowledges are distributed in different courses, and there's no way to combine them together. So finally, I came up with this solution. Yeah, this is the One Student, One Chip initiative. So our goal is to teach on silicon. This is a practical course for undergraduates. We want to let each student have the opportunity to graduate with their own design, with the chips designed by themselves. This is called the one student, one chip. This is Chinese character. Here is one student, one chip. Yeah. So this is the goal of this project. And the first one OSOC was launched in 2019, and 5 senior undergraduates participated. And they completed the design of a 64 RISC-V processor in 4 months, and the chip was taped out. And when the chip was back, and it brought up successfully and can run Linux and also a tiny OS. Actually, this is a teaching OS built by themselves. And this is the 4 months, the process of the 4 months development. Yeah, each color represents one student. And we have actually, they recorded the timeline of the progress. Yeah, for example, here is the TLB is done, and on this time, the process can boot XV6, and in other time, yeah, the process, the CPU can boot Linux, and at that time the process can boot Debian. So this is the whole development process. And finally, the chip was taped out in TSMC, not TSMC, the CMIC 110 nanometer technology, and the chip can run at 200 megahertz to 350 megahertz, and it can run Linux and display the CAS logo. And this is the undergraduate who is defends his PhD, not a PhD, his thesis, undergraduate and bachelor thesis on June 2nd, 2020. So this is the first year one student, one chip initiative, and there were only 5 students, and then we conduct the second OSOC. There were 11 students. And okay, another metric is the cost. We for the first year, the cost is about like 50,000 RMB per student. And for the second OSOC, the cost is reduced to 20,000 per student. And 11 students were from different universities rather than just the UCAS. Yeah, there are some other universities. And among the 11 students, one student actually finally got the PhD program offer from MIT. Another student got the offer from University of Toronto. So yes, yeah, their actually ability was it was improved a lot during this project. And then the third OSOC, we opened to the whole country, and so allow students from other universities to apply for the initiative. And finally, we got about like 760 students applied this project, and those students are from 168 colleges, including 30 overseas universities. Among those students, undergraduates accounts for 50%, and there are also some applicants from companies. Yeah, it's kind of a surprise to us, about like 18. And then we Yeah, in this way, we bring together the chip design education and open source community, the open source chip community. And now we are training them the whole chip design flow, including architecture design, SoC integration, and physical design. And this OSOC also is sponsored actually by many companies, universities, and some research institutes in China. This is the outcome of the third OSOC. So we tape out actually like about like 50 cores. Yeah, each color means one core. So some students can do quite a complicated core. And if we look at the breakdown, so those students are some from EE, and some are from computer science, and even from other majors. Even for there are many undergraduates, even 2 freshmen, yeah. And there are also many master students and some PhD students. And those students can do quite different, I think it's a complicated microarchitecture design. For example, there are among those CPU cores, 12 cores have branch predictors, and 3 cores are out of order. 16 cores are written in chisel, and there are 12 cores, 5-stage pipelines with caches. So this is the outcome, the third OSOC. And now the fourth OSOC is ongoing, and the applicants already exceeds 1,200 from 216 colleges. Yeah, students still accounts for 88%, and 12% are from the industry. Yeah, so how does the OSOC works? I think the key idea is we have 3 stages of the syllabus. We basic, advanced, and specialized. Yeah. So students, the applicants will be classified into the three levels, and we also encourage students to try and study by themselves. Actually, we don't provide the instructions, and we provide them to. We just set goals, and then ask students to explore by themselves. And we also, since there are already more than like 1,000 applicants, so TA teaching assistants are very important. But how can supply so many TAs? Our solution is to recruit TAs from previous OSOC to provide to guide the next OSOC. For example, the third year OSOC, those outstanding students from the third OSOC will be selected to be TA and to guide the fourth OSOC. Yeah. So what will students get? I think the most important is the capability of independent thinking and problem solving. And they can also get knowledge for including the whole chip design flow from spec to architecture design to RTL implementation, SoC integration, verification, synthesis to physical design and to GDS2. And they also will obtain the knowledge of software and hardware co-design by understanding details about how program runs in the computer system stack from application to gate. I think they will also get a real chip. Yeah, and we integrate currently, in order to reduce the cost, we integrate multiple cores into an SoC, and this is just this is really a multi-core, and this is a heterogeneous multi-core in an SoC. And then next we will try like a GDS merge, which means like in a die we can merge multiple GDS design. Okay, that is my talk. So to conclude, is that I think Xiangshan is in the OSOC, the one student, one chip. Both are to get towards the goal of open source chip ecosystem. Yeah, that is my talk. Thank you very much.
Thank you very much. If people has question, please drop in the chat. I have one question about the one student, one chip program. I believe that you developed the entire colloquium for that. You need to put a lot of materials there. The material that you have, it is in Chinese, it is in English. What language you use?
Currently it's in Chinese, and actually we recorded all the process of each student, and every student will write down their progress, and we also give them some talks and some like tutorials. But yeah, currently it's in Chinese. It's and all the videos are in Chinese, but maybe we need to do some like translation.
Yeah, I think that this is a great program, and if you work with different agents, then maybe not translation, maybe to rebuild the material with local experts, with the local materials. This can be, it looks like a great program, and I think that it can be used by many other universities and countries. This is
I think so. Here. We have a website on the OSOC project. So, but currently it's in Chinese. So we probably I think we look for some volunteers to translate into English or other languages. Yeah, it can be translated by even machine learning or machine translation. It's also fun. So the website is online, can be accessed from all over the world. Yeah.
Great. Other questions, Freddy?
No, I don't have any further question. Very nice. Thank you for the presentation.
Great work, and I hope that we can collaborate on this material. It's great work and a great initiative. So
thank you very much.
Thank you very much for your time.
Thank you.
It's quite late in your time. Thank you. And
okay, thank you. Yeah, thank you for reminding me.
The video will be available soon. Thanks a lot.
Thank you very much.
Okay, thank you a lot.
Take care. Bye-bye.
Okay, bye-bye.
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 Bye-bye.